Hi, this is Dan Kelly here. I work at Dalhousie University. I'm a physical oceanographer, and what I'll be showing you here in this video is our Shiny app that tries to elucidate some of the mechanics of a whale being hit by a ship. And I'm speaking to you from in late January of 2024, and yeah, it's a gorgeous day here in Halifax. Fine snow falling like it's a winter wonderland. I love this kind of weather. Okay, so let's just get into it. So I'm showing you here, I'll be going back and forth between two windows. I'm showing you in this window and our studio. The name of the package is Whale Strike, like that. And I'm going to be showing you, there are several apps, but I'm going to show you the one called app2. And I'm just getting help on it by doing !app2. You can see it's version 2 of something. It's, still in development, and so all of this will be maybe changing a little bit. But I just wanted to show you what the app looks like as of now. I guess basically the video can save you, sometimes watching a 5-minute video can save you 45 minutes of thinking. Now I'm in a browser, and it's opened up a tab, this tab, but I'll show you that the other tab is the development site for this. So it's github.com /Dan Kelly /whalestrike. That's the name of it. And if you run into problems, you can raise an issue. And of course, you can look at the code as well. And at the bottom of this, there's like instructions for installing it. You can just copy that by click on this. You could copy it and run it. What this means is that if you don't have remotes installed, you should install remotes first. When I say copy it and run it, I mean run it inside of any kind of an R thing. In this case, it's our studio. And there's a million things you can do. There's a lot of different functions in this. Don't show where I just scrolled that. But the only one I'm showing you here is app2. Okay, so app2. Right, so this is the initial view that you get with this thing. On the left are what I'll call controllers, and on the right is the result of a simulation. Now, the simulation has, and you can adjust any of these things. If you click help, you'll see just a little bit about how that, the thing works. I'm not going to stop to show you that. A pretty nifty thing is that if you click code, it takes whatever view you've got, and I'll show you how to play with the view a little bit, but it shows you code that you could copy and paste into an R session to reproduce the simulation. In other words, this app is kind of a way to tell you how to put this. It's a way to tell you how to work with stuff in code. The main function that's being used is called strike. It takes 3 parameters. Actually, I can't remember. It might have some defaults after this too. The first is a time sequence. It's setting a time sequence from 0 to 1 second, and it's going to have 2,000, I'll say, samples in there. It's running an ODE solver, ordinary differential equation solver, and it's the one called LSODA in the package called DE tools, and it actually uses a time step much smaller than the time step that's dictated. This is just the printing, or in this case, the plotting time step. Okay, so I'll just dismiss that. Right, so I'm going to explore these a little bit in a moment, but of course, quitting quits it. So let's see, so we have 3 panels here. This one is the one on the left, in the middle, and the right. Okay, the one on the left, they're all time series, okay? So it's showing 1 second of simulation. Maybe that's what I'll do first, is I can change that to 0.9 seconds or to 1.55 seconds. So it's just changing the time axis. That's what's happening there. Okay, and the other thing that you can do is you can change the ship speed. Maybe what I'll do now is I'm just going to show you the first plot. So if you click on plot here, you can control what plots appear. And I'm going to make what's called section go away, one called lethality index go away. So we just have one plot that's left there. All right, so here's what's happening. The dotted line is indicating a ship, and that ship is initially going at 10 knots. Okay, so fishing people and nautical people use this weird thing called knots. It took me a while to get used to even saying that without throwing up in my throat a little bit, because it's a non-SI unit, but that's what they use. So that's what the interface is giving. Okay, 10 knots. So this thing is going at 10 knots. What's shown here is the location of the ship. versus time. So in other words, the slope of this thing is the slope that you would get if you have a 10 knot current ship. Sorry, I'm a physical oceanographer. I'll tend to say current by mistake. And this display here is showing you this hypothetical whale. It's only showing a half section of a whale. So this is a particular whale, and you can choose different whale types by clicking in that menu. A particular whale, it's a right whale. It's a whale that people are pretty concerned with in my neck of the woods, which is Eastern Canada. And think of the center of this as being the center of the whale, which I will call a bone layer in the model. There's a bone layer, what's called a sublayer, which you can think of perhaps as organs, etc., and then a layer here of what's called blubber, and then the darker line is the layer of skin. And I have material properties for all of these things, and that's what's happening here. Is okay, so the whale actually goes up to this size, but I'm not showing this sort of the top part of it. All right, so the ship goes along until finally, and this is the prow of the ship, the front of the ship. Finally, it touches onto the whale. And at that moment, two things happen. One, the ship slows down a little bit. Two, the whale starts accelerating in that direction. It's being hit. And three, the whale's material starts squeezing. And I think you can see that the distance between this thickness of this sublayer, which has a certain compressibility, which is a settable parameter, that thickness decreases here. So it's the vertical thickness, the thickness in this direction. So what that means, it's being squished, and there's a force associated with that. And it's that force that slows the ship down. And in fact, this ship, I think, quite appreciably is slowing down. Okay, so let me just go back. That was the first panel. I'm going to turn on the other two panels so you can see them. I hope you can see that what's happening is that when you click one of these things, I'm calling them panels at the moment, more controllers come up. So that's what I did. I chose the plot that way. All right. Okay, so this middle diagram is really the same as the first diagram, except that it's using a coordinate system that's fixed with the whale, if you want to think of it that way. So that the bone, this would be the center of the bone, is always at the top of this diagram. And this one lets you see much more clearly. I'm just going to reduce the maximum time there to get this sort of the collision event to be more or less centered in the window. There we go. So it's centered between 0.2 seconds and 0.6 seconds in this simulation. Okay, so I think you can quite clearly see that this, what I'm calling sublayer, and the positioning is not good. I should probably think of different ways of trying to position this, but I mean, it's hitting into the simulation. But anyway, this doesn't matter that much. Kind of thing I worry about, but it doesn't matter. I'm trying not to use color for this. Maybe I should use color for it, actually. Okay, so you can see the sublayer is squishing. It's squishing. Now, what we've done, and this is in a paper by, I think I can go back to the, sorry, where this one, sorry. Right, so back to the webpage. We have a paper, myself, James Vlasic, and Sean Brillant have a paper that came out in that journal in 2020. It was using this code and other stuff. The other stuff, and this is really important, is that James and Sean acquired a database of ship strikes. And in the database, it's from the literature. And in the database, there's some information on the type of ship, not usually enough information. So James had to do quite a lot of detective work to find that out. We need to know the mass of the ship and the shape of the ship and so forth. Yes, and also some indication of the damage to whales. Now, sometimes that damage is recorded as some damage or whatever, and we had to make some judgments as to, and sometimes it would say, we killed the whale. So we made, you could read the paper, but you should read the paper. So somehow what we did was we came up with the criterion, and in the criterion, the criterion is basically based on stress that's associated. That's the force per area. This thing is being squished. Think of the sole of your shoes. If you have running shoes, they depress a little bit when you stand up in them, and when you're running, they depress a little more. Anyway, that depression, the amount of depression is what we've kind of calibrated. in order to get this thing, which we're calling a lethality index. And it's an index, we make it go from 0 up to unity. 0 to 1 is what I mean. And we're in this index, we use a kind of a logistic regression. And in this index, it appears from the data that we have that if the collision involves an index higher than 1/2, 0.5, that it's likely to get a fatal outcome, that the whale will be killed, injured enough that it would die either at the moment or later on. I mean, quickly later on. And this is colorized in black. So when you see this a little thicker and above this, I think it looks like a dotted line to me. My eyes aren't the best. It might be a gray line. I wrote the code a little while back. When it's higher than that, that indicates a fatality. So we could actually start doing this for science. So this is 10 knots. I've just clicked on that speed and I pressed my arrow to the left. So it's 9.9 knots. I've got the slider set up to go by 0.1 knots. And you could do that, or you could just slide it. And as you slide it, it sort of keeps up with the sliding. Depends how fast your computer is. But okay, so I'm trying to find the maximum speed, which would be just below the limit. It looks like it's 6.6 knots for that ship. Now let's go into the ship. And this is for a small sailing boat, actually. Fishing boat at 45 tons. And what I'm going to do now, I want you to look at the right-hand panel, just this one. Maybe that's the only one I'll show. Why not just do that? Danny boy. Okay, so there we go. Right, I'm going to make it more massive. You can see that now we're at 300 tons. It's clearly a problem. If I go down to, I guess I started at 45. Let's go down to 30. We'll go down to, so we're significantly below the threshold in this case. I'll go back to the plot and we'll just check out the location as well. And you can see that in this case, not only is it not fatal, but these are heavy whales, right? The boat would bounce off the whales. So I think this would almost certainly be detected by the people on the boat. Right, but this is kind of a little bit of a going around the harbor sort of a speed. And one of the conclusions that you'll see in the paper is that even for small, go back to the 45 ton, if I can get it there. Yeah. Even for a small vessel like that, by the way, there's also things for the impact, to describe the impact. So this is the height of the impact zone and the width of the impact zone, width and height. And we calculated that for some different shapes. But if you have a ship in mind, you will want to insert numbers for that. Actually, let me just try something. So I'm going to make that width from 1.15 meters to be just 0.5 meter. And you see that now it's lethal. The same force is being applied for a smaller area. It's the pressure that stresses force per area, but it's also pressure, same thing. And it's causing the compression, which is causing the damage. I'll make it just be like 10 centimeters wide. And that would be a dagger board on a sailing boat, say. And that is, lethal even at the speed here. So such a boat with such a sharp prow. I don't even know if it's going at 1 knot. Let's check out 1 knot. Okay, 1 knot's okay. 3 knots. Yeah, it could be going a couple of knots, but basically please just don't have it's almost like a knife hitting the whales 10 centimeters wide. What else can I show you? I think that was the main thing I wanted to show you in this. You can make all the controls go away like that if you want. But if you do that, then you can't adjust anything. Let's see, bring that back. I will probably be adding some things. Like I'll probably add, maybe I'll just tell you, I'm going to type a question mark. When I do that, it detects that keystroke and it shows the help that you can also get the same help by clicking this. But I think I might make it such that we could have a small ship. I'd have to decide what to code them, but a single letter for that, maybe an S for a small ship and an L for a large ship. And what those things could do is they could preset these things. Not sure I want to do that, but I might do that. Right. I think that's what I wanted to show you. Thanks for listening to my mumblings and my ummings and awings. The point of this basically is I think it might be a little more helpful to you than reading through the documentation. It's also documented. I'm just going to go back to where I was. Over here on the right, you can see all the documentation. So there's all these different functions in here. You can see what each of these functions does, just picking a random one here. You can see a formula that's being applied, some references and so forth. And there's also a little thing about getting started with the package. And most of this is on non-GUI use, like not the thing that I just showed you, but writing code. And any serious work, I think almost always will involve writing code like this. But like I say, if you go back to the thing here, you can always just look at the code here because that's been updated now to show you the thing which I just showed you. Right, thanks for watching and take care.